In February 2023, a small team of astronomers sat down to look through some of the very first images James Webb Space Telescope had ever captured, and one of them, staring at a tiny patch of sky near the Big Dipper, spotted something that made her stop and double-check her math. Certain she'd made a mistake. She hadn't. What she and her colleagues had found were galaxies that, according to everything we thought we understood about how the universe works, simply should not exist. In this video, we're going to walk through exactly what James Webb found, why it genuinely alarmed cosmologists around the world, what's happened in the years since as scientists have worked to explain it, and where this still unfolding story stands today. If you enjoy real, documented space science rather than exaggerated claims, stick around till the end. This particular story is worth telling carefully because it's a genuinely rare example of a discovery that lived up to its dramatic framing, at least initially, while also demonstrating exactly how science is supposed to work when confronted with a result this disruptive. Unlike a lot of clickbait space content that throws around phrases like "shouldn't exist" loosely, actual working cosmologists used almost identical language in peer-reviewed papers and in interviews to describe their own genuine confusion when they first encountered this data. That's part of what makes this such a compelling case study in real, ongoing scientific discovery. Let's start with some essential background, because understanding why this discovery was so shocking requires understanding what astronomers expected to find in the first place. The standard model of cosmology, the framework nearly all modern astrophysics is built on, describes how the universe evolved from the hot, dense conditions right after the Big Bang into the vast, galaxy-filled cosmos we observe today. Under this model, galaxy formation is a gradual, hierarchical process. Small clumps of matter, pulled together by gravity in the early universe, slowly merge with other small clumps over hundreds of millions, even billions of years, eventually building up into the large, mature galaxies we see relatively nearby, like our own Milky Way. Under this framework, galaxies in the very early universe, forming within the first few 100 million years after the Big Bang, were expected to be small, young, and still actively assembling themselves out of primordial gas. This standard model, often referred to by cosmologists using the shorthand lambda CDM, short for lambda cold dark matter, has been remarkably successful at explaining a huge range of independent astronomical observations, from the detailed patterns in the cosmic microwave background radiation left over from the Big Bang, to the large-scale distribution of galaxies across the observable universe, to the observed rate at which the universe is expanding. Because this model has passed so many other rigorous tests over the decades, any observation that appears to genuinely conflict with its predictions carries significant scientific weight and gets scrutinized extremely carefully before anyone concludes the model itself might need revision. James Webb Space Telescope was specifically built, in large part, to look deeper into this early era of the universe than any previous telescope could manage, using its powerful infrared instruments to detect the faint red-shifted light from galaxies that existed when the universe was just a few 100 million years old. When astronomers pointed Webb at a patch of sky as part of its Cosmic Evolution Early Release Science Survey, nicknamed SEERS, and began analyzing the very first data the telescope sent back, they were looking specifically for these young, still-forming galaxies, expecting to see exactly the kind of small, faint, early-stage structures the standard model predicted. Erica Nelson, an astrophysicist at the University of Colorado Boulder, was one of the researchers combing through this early data. While examining a postage stamp-sized section of one of Webb's deep-field images, she noticed a handful of small, fuzzy, reddish dots that appeared far too bright to make sense. Working with colleagues, including Ivo Labe of Swinburne University of Technology in Australia, the team analyzed the light from these objects in detail and determined they were looking at galaxies that existed when the universe was only somewhere between 500 and 700 million years old, less than 5% of the universe's current age of roughly 13.8 billion years. That timing alone wasn't the shocking part. Astronomers already knew galaxies could exist this early, since Webb and other instruments had previously spotted galaxies from similarly ancient eras. What stunned the research team was just how massive and mature these particular galaxies appeared to be. Rather than looking like small, young, still assembling clumps of stars and gas. Light coming from these objects suggested they already contained nearly as many stars as our own Milky Way galaxy does today, a galaxy that took over 13 billion years to build up its current stellar population. One of the candidate galaxies appeared to potentially contain the equivalent mass of 100 billion suns worth of stars, an almost unbelievable amount of stellar material to have assembled in such a comparatively short window of cosmic time. Nelson's reaction to the finding became something of a memorable quote within the astronomy community. "It's bananas," she said, describing the fundamental problem the team faced trying to make sense of what they were seeing. As she explained it, you simply don't expect the early universe to have been able to organize itself this quickly. Under the standard hierarchical model of galaxy formation, small structures need time, real physical time measured in hundreds of millions of years, to gradually merge and grow into something this large. These galaxies, according to the team's analysis, simply shouldn't have had enough time to form. The scale of the problem became even clearer when the team ran the numbers more carefully. Ivo Labbé pointed out that if you actually add up the total stellar mass implied by the brightness and characteristics of these 6 candidate galaxies, the number would exceed the total amount of matter that standard cosmological models say should have even been available to form stars and galaxies in the universe at that particular point in cosmic history. In other words, this wasn't simply a case of galaxies growing unusually fast. The numbers, at face value, suggested there wasn't even supposed to be enough raw material in existence yet to build structures this massive in this particular region of space, at this particular moment in the universe's development. This is worth emphasizing because it represents a genuinely different and in some ways more serious category of problem than simply finding galaxies that grew faster than expected. A galaxy growing unusually quickly might be explained by some unusually efficient, if still fundamentally conventional, formation process. But finding galaxies that appear to require more raw material than cosmological models say should have existed at all in that region of space, at that specific time, points toward something potentially more fundamental being incomplete or incorrect in the underlying theoretical framework rather than simply an unusually efficient version of a process scientists already understood. The team published their findings in the journal Nature in February 2023, and the response from the broader scientific community was a mixture of genuine excitement and equally genuine unease. Findings this disruptive to a well-established, heavily tested scientific framework don't come along often, and researchers understood immediately that if these galaxies really were as massive as the initial data suggested, something meaningful would need to change about how scientists understand the early universe, potentially even challenging aspects of the broader standard cosmological model itself, a model that has otherwise proven remarkably successful at explaining a huge range of other observations about the universe. It's worth pausing here to explain exactly why standard cosmological theory struggles so much with galaxies, this massive, appearing this early. The prevailing model describes matter clumping together gradually through a process where smaller structures merge step by step into progressively larger ones, a bit like small droplets of water gradually combining into bigger and bigger puddles rather than an entire lake appearing all at once. This gradual merging process takes time, and cosmologists have detailed simulations modeling roughly how much mass should be able to accumulate into galaxy-sized structures within any given window after the Big Bang. Galaxies as massive as the ones Lebbe and Nelson's team identified, appearing within the universe's first 700 million years, represented a serious departure from what these simulations predicted should be physically possible within that time frame. To put this time frame in perspective, 700 million years sounds like an enormous span of time from a human point of view, but on cosmic timescales relevant to galaxy formation, it's remarkably brief. Our own Milky Way took the better part of the universe's entire 13.8 billion-year history to build up its current population of several 100 billion stars through countless mergers and prolonged periods of ongoing star formation. Finding galaxies with comparable stellar populations already assembled within less than 5% of that total time span is roughly equivalent to expecting a forest to grow to full maturity within the first few weeks after the seeds were planted. The fundamental biological, or in this case astrophysical, processes involved simply aren't understood to work that quickly under normal circumstances. Astrophysicist Joel Leja of Penn State University, one of the co-authors on the original study, explained that researchers had gone into this kind of deep field observation with fairly specific expectations about what kind of galaxies should exist this early in cosmic history, namely that they should be young and comparatively small. Finding galaxies that instead looked shockingly big and containing stars that appeared surprisingly old for how early in the universe's history they were observed directly conflicted with those expectations and didn't match up cleanly with earlier observations that had been made using Webb's predecessor telescope, Hubble, which lacked the infrared sensitivity necessary to fully characterize objects this distant and this faint. Given the magnitude of this apparent contradiction, scientists proposed several possible explanations, understanding that any of several different factors, or some combination of them, could ultimately be responsible for what the team had observed. One possibility researchers raised early on was that there might be some entirely new, previously unrecognized pathway for galaxy formation, some kind of fast-track mechanism that could allow matter to organize into large galactic structures far more rapidly than the standard, gradual merging process would normally allow. Lebbe described this possibility somewhat vividly, suggesting there might be a distinct formation channel capable of producing what he called monsters, unusually massive galaxies that simply don't follow the typical, slower assembly process most galaxies go through. A second major possibility, raised by astronomer Emma Curtis Lake of the University of Hertfordshire, who wasn't part of the original study but reviewed its implications, involved black holes. Some of these apparently massive, bright galaxies could actually contain supermassive black holes at their centers, actively pulling in surrounding gas and dust. As material falls into a black hole, it heats up dramatically and emits enormous amounts of light, in some cases outshining the combined light of every star in the surrounding galaxy. If some portion of the light Webb detected from these objects was actually coming from active black holes rather than from starlight alone, that could make a smaller, less massive galaxy appear far brighter, and therefore far more massive than it actually is when analyzed using standard assumptions about what's producing the observed light. This kind of misidentification is a genuinely well-understood challenge in observational astronomy, even outside the context of this specific mystery. When astronomers estimate a distant galaxy's total stellar mass, they typically rely on measuring its overall brightness and color, then using established models to infer how many stars and what kind of stars would be needed to produce that particular combination of light. This method works well for typical galaxies, where starlight is the dominant source of the observed brightness. But it can break down significantly for galaxies containing an actively feeding supermassive black hole, since the extra light contributed by material heating up as it falls toward the black hole gets mistakenly attributed to starlight in the standard analysis, inflating the galaxy's estimated stellar mass well beyond its true value. This second possibility turned out to be a genuinely important thread that researchers spent the following years carefully investigating, and it's led to some real meaningful progress in understanding what's actually going on. In a follow-up study published in the Astronomical Journal, Katherine Chwarowski, a graduate student at the University of Texas at Austin, working under Stephen Finkelstein, who led the original Sears survey that provided much of this data, took a much closer look at a broader sample of these apparently oversized early galaxies to figure out how many of them could be explained by this black hole contamination effect. Chwarowski's analysis found that a meaningful portion of these unusually bright, seemingly oversized early galaxies were indeed affected by exactly this kind of black hole activity, sometimes called an active galactic nucleus. In these specific cases, once researchers accounted for how much of the observed brightness was actually coming from material heating up as it fell into a central black hole, rather than from starlight produced by a genuinely enormous population of stars, the implied stellar mass of the galaxy dropped considerably. Some of these galaxies, once properly corrected for this effect, turned out to be significantly less massive than the initial, more straightforward analysis had suggested. This doesn't mean the entire mystery has been fully resolved, and it's important to be precise about exactly what this follow-up research did and didn't show. As Chwarowski herself put it, summarizing the current state of the research, astronomers are still seeing more early massive galaxies than standard cosmological models predict, even after accounting for the black hole contamination effect in a meaningful subset of cases. However, none of the remaining galaxies in the corrected sample appear to be so massive that they completely break the fundamental predictions of the standard cosmological model the way the very earliest, most dramatic estimates had initially suggested. In other words, the mystery has been meaningfully narrowed and partially explained, but a real, measurable excess of unusually massive early galaxies still remains, one that current models don't fully account for. This evolving, still unfolding story is genuinely representative of how real scientific progress tends to work, especially with a discovery this disruptive to an established framework. The initial 2023 findings generated legitimate alarm within the cosmology community, precisely because they appeared to directly challenge the standard model in a way few observations ever had. Rather than either fully confirming a crisis in cosmology or completely dismissing the finding as an error, subsequent research has done what careful science typically does, identified a real contributing factor, in this case active black holes inflating some galaxies' apparent brightness and mass, while still leaving a smaller but genuinely puzzling residual excess of unusually massive early galaxies that researchers continue actively working to explain. It's also worth mentioning a separate related discovery that adds another layer of genuine strangeness to this broader story. In a study published in 2024, led by Ben Forrest of the University of California, Davis, astronomers using Webb identified a massive galaxy formed less than 2 billion years after the Big Bang that appeared to show essentially no rotation at all. This is significant because galaxies of this size and maturity are normally expected to be actively spinning, a natural consequence of how they gradually assemble their mass from a rotating disk of surrounding gas and dust. Finding a galaxy this massive with no measurable rotation at such an early point in the universe's history represented yet another unexpected departure from standard expectations about how galaxies of this type are supposed to behave and evolve, adding further weight to the broader sense that the early universe was producing structures that don't cleanly fit existing theoretical models. Forrest and his colleagues noted that this lack of rotation is a trait normally associated only with much older, more evolved galaxies, found much closer to our own cosmic neighborhood, galaxies that have had billions of years for internal processes to settle their stellar orbits into whatever final configuration they end up with. Finding this same characteristic in a galaxy that formed so early in the universe's history suggests that some early galaxies may have gone through their formation and internal evolution far more rapidly than standard timelines would predict, echoing the same broader theme running through the massive early galaxy puzzle, that at least some structures in the early universe appear to have matured much faster than existing models account for. These findings, taken together, illustrate why this particular area of astrophysics has remained such an active, closely watched field of research since Webb's earliest observations began in 2022. Every new deep field survey, every additional galaxy candidate identified and carefully characterized, adds another data point to an ongoing, genuinely unresolved scientific conversation about exactly how quickly and through what specific physical mechanisms the early universe was capable of assembling massive galactic structures. Let's talk about why this matters beyond simply being an interesting curiosity for astronomers to puzzle over. The standard cosmological model isn't just a theory about galaxy formation specifically, it's a comprehensive framework that also explains the large-scale structure of the universe, the cosmic microwave background radiation left over from the Big Bang, the observed abundance of light elements like hydrogen and helium, and a wide range of other independently verified observations. If it turns out that galaxy formation in the early universe genuinely doesn't match what this model predicts, even after accounting for factors like black hole contamination, that could point toward the need for meaningful revisions to some part of this broader framework, potentially involving how dark matter behaves, how efficiently early gas clouds were able to collapse and form stars, or some other fundamental aspect of early cosmic evolution that current models don't yet fully capture. Some researchers have proposed that the explanation might not require revising dark matter or the broader cosmological framework at all, but might instead point towards star formation itself being simply more efficient in the early universe than current models assume. Under this idea, early gas clouds might have been able to convert into stars considerably faster and with less energy lost to processes that normally slow star formation down, like radiation pressure or stellar winds pushing gas away before it can collapse into new stars. If early star formation really was unusually efficient, that could allow galaxies to build up large stellar populations more quickly than standard models currently predict, without necessarily requiring any change to how dark matter or the overall large-scale structure of the universe actually works. At the same time, it's worth maintaining appropriate scientific caution here, because a genuinely significant portion of the initial universe-breaking claims from 2023 have already been meaningfully tempered by the more careful, more detailed follow-up analysis conducted in the years since. This is exactly the kind of self-correcting process science is supposed to go through when it encounters a genuinely surprising result. Initial excitement and alarm, followed by careful, methodical investigation into alternative explanations, followed by a more nuanced, evidence-based understanding that neither fully confirms the most dramatic initial interpretation nor completely dismisses the underlying anomaly. Let's address a few common questions people tend to have about this ongoing story. Does this mean the Big Bang Theory itself is wrong? No. Nothing about this finding challenges the basic evidence for the Big Bang itself, which rests on multiple independent lines of evidence completely separate from galaxy formation timelines, including the cosmic microwave background radiation and the observed expansion of the universe. What's being questioned and refined is a more specific piece of the broader cosmological framework, specifically how quickly and through what mechanisms galaxies were able to assemble large amounts of stellar mass in the universe's earliest few hundred million years. Has this mystery been completely solved at this point? Not entirely. As Chwarovski's research demonstrated, a meaningful portion of the apparent impossible mass has been explained by black hole contamination, inflating the observed brightness of some galaxies. But researchers are still finding more early massive galaxies than standard models predict, even after this correction, meaning there's still a real unresolved excess that continues to be actively studied. Could this eventually lead to major changes in how scientists understand dark matter or the broader structure of the universe? It's possible, though it's far too early to say with any confidence. Some researchers have proposed that early star formation might have simply been more efficient than current models assume, allowing gas clouds to convert into stars faster than previously thought, without requiring any fundamental changes to how dark matter behaves. Others continue investigating whether more exotic explanations might eventually be needed. This remains a genuinely open, actively researched question, rather than one with a settled answer. Why did it take until James Webb launched to even discover this apparent problem in the first place? Webb's predecessor, the Hubble Space Telescope, simply wasn't sensitive enough in infrared wavelengths to reliably detect and characterize galaxies from this early in the universe's history. Light from these extremely distant galaxies gets stretched, or redshifted, into infrared wavelengths by the time it reaches us. Due to the universe's ongoing expansion, and Webb was specifically engineered with the infrared sensitivity necessary to observe this earliest era of cosmic history, in the kind of detail required to even notice a discrepancy like this one existed. How confident are astronomers in the distance measurements for these galaxies, given how much the entire mystery depends on them being genuinely this ancient? Distance measurements for objects this far away rely on measuring redshift, how much a galaxy's light has been stretched toward longer wavelengths due to the universe's expansion, and Webb's instruments are specifically designed to measure this with high precision. While individual measurements always carry some degree of uncertainty, and some early candidate galaxies from this research have had their exact distances refined or revised as more detailed follow-up observations were conducted. The broader finding that multiple galaxies exist with surprisingly high stellar mass at very early cosmic times has held up across multiple independent research teams and observation campaigns, giving scientists reasonable confidence that this is a genuine phenomenon worth continuing to investigate, rather than simply a measurement error. How confident are astronomers in the distance measurements for these galaxies, given how much the entire mystery depends on them being genuinely this ancient? Distance measurements for objects this far away rely on measuring redshift, how much a galaxy's light has been stretched toward longer wavelengths due to the universe's expansion, and Webb's instruments are specifically designed to measure this with high precision. While individual measurements always carry some degree of uncertainty, and some early candidate galaxies from this research have had their exact distances refined or revised as more detailed follow-up observations were conducted, the broader finding that multiple galaxies exist with surprisingly high stellar mass at very early cosmic times has held up across multiple independent research teams and observation campaigns, giving scientists reasonable confidence that this is a genuine phenomenon worth continuing to investigate, rather than simply a measurement error. So, to bring this all together, what did James Webb actually find that shouldn't exist? It found a set of galaxies from the universe's first several hundred million years that appeared, in initial analysis, to be dramatically more massive and more mature than the standard model of cosmology says should have been physically possible in that amount of time. Years of careful follow-up research have since shown that a meaningful portion of this apparent impossibility can be explained by actively feeding supermassive black holes, making some of these galaxies look brighter and therefore more massive than they truly are. But even after accounting for that effect, a genuine, still unexplained excess of unusually massive early galaxies remains, keeping this one of the most actively debated open questions in modern cosmology. This is, in many ways, exactly the kind of story real science produces far more often than the neat, fully resolved mysteries you tend to see in dramatic headlines. It began with a genuinely alarming discovery that seemed to threaten one of astrophysics' most successful theoretical frameworks. It's been followed by years of careful, methodical investigation that has partially, but not completely, resolved the underlying puzzle. And it remains right now an active area of ongoing research, with astronomers around the world continuing to use James Webb Space Telescope to gather more data, hoping to eventually settle exactly how the early universe managed to build galaxies this large, this early, and whether doing so requires any meaningful revision to our broader understanding of how the cosmos actually works. There's something genuinely fitting about how this story continues to unfold in real time, years after the initial discovery. Unlike a lot of space content that treats every finding as a single, complete, self-contained revelation, this particular mystery has evolved gradually through multiple published papers, competing hypotheses and incremental refinements, exactly the way most significant scientific questions actually get worked out in practice. It's a genuinely useful reminder that the most honest version of a space story is often the one that's still being written, rather than the one wrapped up in a single dramatic headline. If you found this breakdown interesting, make sure to like this video, subscribe to the channel, and let us know in the comments. Do you think the remaining mystery of these oversized early galaxies will eventually be fully explained within the standard model of cosmology, or do you think it points towards something genuinely new that scientists haven't figured out yet? See you in the next video with another real, grounded space story worth exploring.